standard base velocity measures the target's velocity with respect to Earth's surface, which is stationary. However, storms and storm scale phenomena, like tornadoes, almost always move with respect to Earth's surface. Base velocity estimates the portion of a target's velocity that's moving directly toward or away from the radar, i.e. along a radial. This also includes the motion of the parent storm, which can make it difficult to obtain proper velocity measurements. For example, if a target within a storm has a velocity of 40 miles per hour, in essence the storm has 40 mile per hour winds, and the storm is moving directly at the radar at 30 miles per hour, the base velocity product will estimate the target's velocity to be 70 miles per hour, which is erroneous. This can mask rotational signatures like TVSs, making them difficult to analyze properly. To combat this, we can use a product called storm relative velocity. This is just like the base velocity product, only with storm motion subtracted out. So, in our example of a target moving at 40 miles per hour within a storm moving directly at the radar at 30 miles per hour, the storm relative velocity product would estimate that target's velocity to be a more accurate 40 miles per hour because storm motion has been subtracted out. Storm relative velocity is especially effective in identifying TVSs in QLCSs, as well as in situations in which supercells are moving very quickly. Let's take a look at an example. On the left is base reflectivity, and on the right is base velocity. Here we have a supercell thunderstorm moving at 55 miles per hour away from the radar site, which is located just off the bottom left corner of the image. As you can see, the supercell possesses a well-defined hook echo, as denoted by the yellow arrow. At the tip of the hook, we see an area of strong outbound winds, but very little in the way of inbound winds. At first glance, you might overlook this signature given its asymmetric nature, but when we switch to storm relative velocity, we see a much clearer depiction of a TVS, with an area of strong inbounds adjacent to an area of strong outbounds.
The Chaser Academy is our premium subscription, and it's the best deal in storm chasing. Link in the description.
This makes sense. Let's say our inbound winds within this TVS have a velocity of 55 miles per hour moving toward the radar. With a storm motion of 55 miles per hour away from the radar, the resultant base velocity reading would be an erroneous 0 miles per hour, and our outbound velocities would be drastically overestimated. With storm motion factored out, we get a much more realistic depiction of the velocities within the couplet and a much clearer indication of a TVS. At the time of this radar image, an EF3 tornado was ongoing, which highlights the importance of using storm relative velocity rather than base velocity in tornadic situations. In addition, TVSs within QLCSs can sometimes be difficult to ascertain given their typically weak and brief nature. While this can be the case regardless of the velocity product used to analyze them, storm relative velocity can help in this regard. Base velocity is more effective in identifying straight-line wind gusts, including downbursts, particularly at the lowest elevation angle.
Remember to check out those links in the description below, and then watch another video.